Depth-based visual predictive control. Visual servoing is a technique in which we utilize the feedback information provided with a visual sensor to control the motion of a robot. There are two classic visual servo control approaches, image-based visual servoing and position-based one. In IBVS, there is no need to the camera pose estimation or external calibration, and consequently there is no need to the target's 3D model, but we may have the singularity problem, camera retreat or advanced problems, and local minima. On the other hand, in PBVS, although the system is globally asymptotic stable and we have direct control over the camera motion in the Cartesian space, but a precise model of the target is required and the controller is really sensitive to the camera calibration errors. In addition, the target may leave the camera's field of view. Generally, there are different constraint categories in the visual servoing, such as visual, robot-related, control-related, and task-related constraints, which must be addressed in any successful application of visual servoing. So we decided to utilize the model predictive control method, which has the superior performance in constraint handling. On the other hand, to make the system robust in presence of the uncertainties and modeling errors, the existing predictive controller has been embedded into internal model control structure. Similar to other MPC method, depth-based visual predictive controller has four essential elements. The first element is the reference signal, which is the multiplication of the target point's depth expressed in the camera frame and the corresponding homogeneous coordinate of it. The second one is a linear predictive model of the dynamic process as shown in the figure. The third element is the cost function, which should be minimized in order to obtain the optimized control input. The cost function here is the sum of the norm of depth-based features error. Finally, we employ the sequential quadratic program to minimize the cost function in presence of the existing 2D depth and control constraints as demonstrated here. As it was mentioned before, one of the issues in IBVS and also in its predictive equivalent IVPC is camera retreat or advanced problems. These issues emerge when there is a large amount of pure rotation around the optical axis. In Chomet conundrum, which is the 180-degree pure rotation around the optical axis, the control procedure of a free-flying camera by IVPC will fail due to having unbounded retreat or advanced problems. In DVPC, due to having direct control over the target point's depth, the camera rotates 180 degrees successfully. On the other hand, in PVPC, due to having no direct control over the 2D visual features, they may leave the camera's field of view. This issue will be resolved in DVPC due to having direct control over 2D coordinates of the visual features. To verify the performance of the proposed DVPC, a 3-degree of freedom catheter as a continuum robot has been modeled by utilizing the constant curvature method. The corresponding Denavit-Hartenberg parameters are shown in the following table. As it was expected, by increasing the prediction horizon, the 2D visual trajectories became smoother and the pressure on the system's actuators became less, while all of the existing constraints were met. In order to verify the robustness of the controller in presence of the system uncertainties and modeling errors, the camera measurement, the control inputs, and the camera intrinsic parameters are polluted by the following errors. As it's demonstrated, due to having the internal model control structure, the system was robust and the camera converged to its final destination successfully. The developed DVPC method has been also employed to control a 6th degree of freedom manipulator from denser robotics. As it was expected, by increasing the prediction horizon, the 2D visual trajectories became smoother. On the other hand, as it can be seen in the following diagrams, the existing depth error will be compensated faster by increasing the prediction horizon. Finally, as it's depicted in these figures, due to having direct control over the target point's depth expressed in the camera frame, the amount of camera's retreat became less by increasing the lower bound of the depth constraint. Thank you for your attention.